Welcome to Quantumize. I'm thrilled to have you here today because we're about to embark on one of the most profound journeys in modern physics. Today, we're going to explore a concept that completely revolutionizes our understanding of reality itself: quantum vacuum fluctuations and the Casimir effect. By the end of this video, you'll understand why the very notion of empty space is fundamentally wrong. You'll see how the vacuum, what we think of as absolute nothingness, is actually a boiling sea of energy and activity. And we'll explore the Casimir effect, an elegant experiment that proves this isn't just theoretical speculation, but observable, measurable reality. So grab your favorite beverage, get comfortable, and let's dive deep into the quantum realm. Trust me, what you're about to learn will change the way you see the universe forever. Let's start with a seemingly simple question. What is a vacuum? If I asked you to describe empty space, what would you say? Most people would describe it as nothing, a void, an absence of matter, energy, particles, an absence of everything. It's the ultimate emptiness, right? This intuitive understanding of the vacuum has deep roots in human thought. The ancient Greek philosophers debated whether true emptiness could even exist. Aristotle famously argued that nature abhors a vacuum. He believed that empty space was impossible, that something must always fill the void. Other philosophers, like Democritus and Leucippus, proposed that atoms moved through empty space, suggesting that voids were not only possible but necessary. Fast forward to the scientific revolution, when Evangelista Torricelli created the first sustained vacuum in 1643 using his mercury barometer. It sparked intense debate. What exactly existed in that space above the mercury? Was it truly empty, or was it filled with some invisible substance? By the 19th century, physicists had a new answer: the luminiferous ether. This hypothetical medium was proposed to fill all of space, serving as the medium through which light waves propagated. Just as sound waves need air to travel through, scientists reasoned that light waves must need some medium too. The vacuum, in this view, wasn't empty at all. It was filled with ether. But then came the Michelson-Morley experiment in 1887. This brilliant experiment attempted to detect Earth's motion through the ether by measuring differences in the speed of light in different directions. The result? Nothing. No difference was detected. The ether hypothesis began to crumble. Einstein's special relativity in 1905 delivered the final blow. Light didn't need a medium to propagate through. Space could be truly empty, or so it seemed. Einstein's equations worked perfectly well with a vacuum that contained absolutely nothing. For a brief moment in physics history, we thought we had our answer. A vacuum was simply empty space. No matter, no energy, no fields, no nothing. It was the baseline, the zero state, the cosmic canvas upon which reality painted itself. But then quantum mechanics arrived, and everything changed. The early 20th century brought a revolution in physics that would reshape our understanding of reality at its most fundamental level. Quantum mechanics emerged from a series of puzzling observations that classical physics simply couldn't explain. The ultraviolet catastrophe, the photoelectric effect, atomic spectra, and the bizarre behavior of particles at microscopic scales. At the heart of quantum mechanics lies a principle that would prove crucial to understanding the vacuum: Heisenberg's uncertainty principle. In 1927, Werner Heisenberg discovered that certain pairs of physical properties cannot both be known with arbitrary precision simultaneously. The most famous pairing is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. But there's another pairing that's equally important and perhaps even more profound: energy and time. The uncertainty principle states that the uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to Planck's constant divided by 4 pi. Mathematically, we express this as del T times delta T greater than or equal to /2, whereas the reduced Planck constant. Now, what does this mean in practical terms? It means that if you observe a system for only a very short time interval, there can be a large uncertainty in its energy. In other words, energy doesn't have to be precisely conserved over extremely short time scales. The vacuum can borrow energy as long as it pays it back quickly enough. This might seem like an abstract mathematical curiosity, but the implications are staggering. It means that even in a perfect vacuum, a region of space with no particles, no radiation, absolutely nothing, energy can still fluctuate. Virtual particles can pop into existence, borrowing energy from the vacuum itself, as long as they disappear again within a time interval allowed by the uncertainty principle. Let me give you a concrete example. An electron has a certain mass, which via Einstein's E equals mc squared corresponds to a certain energy, about 511 keV. For an electron-positron pair to spontaneously appear, they need to borrow about 1.022 MeV of energy total. According to the uncertainty principle, they can do this, but only for an incredibly brief moment, about 6 times 10 superscript 2 superscript 2 seconds. That's 0.000000000000000006 seconds. In that incomprehensibly short time, the particle pair must annihilate and return the borrowed energy to the vacuum. These aren't real particles in the conventional sense. We call them virtual particles. They don't last long enough to be directly observed or measured. They exist in a quantum superposition state, a ghostly limbo between existence and non-existence. Yet, as we'll see, their effects are very real and measurable. The quantum vacuum, therefore, is nothing like the empty void we imagined. It's a seething sea of activity, with particle-antiparticle pairs constantly winking in and out of existence. Electrons and positrons, quarks and antiquarks, photons, gluons. Every type of particle allowed by physics is constantly being created and destroyed in a cosmic dance of creation and annihilation. Think of it like a financial analogy. Imagine a bank that allows you to take out a loan, but the larger the loan, the faster you must repay it. You could borrow $1 million, but you'd have to pay it back in a microsecond. You could borrow $1 billion, but you'd have to pay it back in a nanosecond. As long as you repay fast enough, you can borrow as much as you want. The quantum vacuum operates on similar principles, except instead of money, it's borrowing energy, and instead of microseconds, we're talking about time intervals so short they make a microsecond seem like an eternity. To truly understand vacuum fluctuations, we need to delve into quantum field theory, or QFT. This is the framework that combines quantum mechanics with special relativity, and it's arguably the most successful scientific theory ever devised. The predictions of QFT have been confirmed to extraordinary precision, in some cases to better than 1 part in a billion. In quantum field theory, we stop thinking about particles as little billiard balls moving through empty space. Instead, we think of fields, quantum fields that permeate all of space and time. There's an electron field, a photon field, a quark field, and so on for every type of particle. These fields are fundamental. Particles are merely excitations or vibrations in these fields. Imagine a vast ocean stretching infinitely in all directions. The water itself represents a quantum field. Most of the time, the ocean is relatively calm. This is the vacuum state. But occasionally, waves appear on the surface. In quantum field theory, these waves are particles. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. But here's the crucial insight. Even when the ocean appears calm, it's never perfectly still. There are always small fluctuations, tiny ripples and disturbances, even when no large waves are present. These are the quantum fluctuations of the field, and they exist even in the vacuum state, the lowest possible energy state of the field. In classical physics, the lowest energy state means complete stillness. Zero energy, zero activity. But in quantum field theory, the uncertainty principle prevents this. The fields can never be perfectly still. They're always fluctuating, always jittering with zero-point energy. This zero-point energy is mind-boggling when you calculate it. In principle, there are an infinite number of possible fluctuation modes at all possible wavelengths. When you add up all these fluctuations, you get an infinite energy density for the vacuum. This is called the vacuum catastrophe or the cosmological constant problem, and it's one of the greatest unsolved problems in theoretical physics. Now, you might reasonably ask, if the vacuum has infinite energy, why doesn't it collapse into a black hole? Why don't we observe this energy gravitating? The answer is complicated and not fully understood. What we typically do in calculations is use a procedure called renormalization, where we subtract away the infinite part and focus on differences in vacuum energy between different situations. This mathematical trick works remarkably well for making predictions, even though the underlying physical picture remains puzzling. What we can say definitively is that vacuum fluctuations are real and measurable. They're not just mathematical artifacts. They have observable consequences, which brings us to several important phenomena. First, let's talk about the Lamb shift. In 1947, Willis Lamb discovered that certain energy levels in the hydrogen atom that should be identical according to Dirac's equation actually differ slightly. The 2s/2 and 2p/2 states, which should have the same energy, are actually separated by about 1057 megahertz in frequency. What causes this splitting? The answer is vacuum fluctuations. The electron in the hydrogen atom is constantly interacting with virtual photons from a vacuum. These virtual photons cause the electron to jiggle slightly. We call this the Zitterbewegung or trembling motion. This jittering affects how the electron interacts with the proton's electric field, slightly shifting the energy levels. The effect is small but measurable, and it matches the predictions of quantum electrodynamics with stunning precision. Similarly, vacuum fluctuations contribute to the anomalous magnetic moment of the electron. The electron's magnetic moment isn't exactly what you'd predict from Dirac's equation. There's a small correction factor called the G factor. The measure value is approximately 2.00231930436 with incredible precision. This tiny deviation from 2 is due to the electron constantly emitting and reabsorbing virtual photons, as well as interacting with other virtual particles. The theoretical calculations, which include contributions from vacuum fluctuations, agree with experiment to more than 10 decimal places. This is one of the most precise confirmations of any theory in science. Vacuum fluctuations also explain spontaneous emission. When an atom is in an excited state, it will eventually decay to a lower energy state by emitting a photon, even if there are no external photons around to stimulate this emission. Why does this happen? The vacuum fluctuations of the electromagnetic field provide the perturbation that triggers the emission. The atom interacts with virtual photons in the vacuum, and this interaction causes the spontaneous decay. Let's dive deeper into the concept of virtual particles, because they're central to understanding both vacuum fluctuations and the Casimir effect. Virtual particles are one of the most misunderstood concepts in quantum physics, often portrayed in popular science as literal particles that pop in and out of existence. The reality is more subtle and more fascinating. In quantum field theory, virtual particles appear as internal lines in Feynman diagrams, those iconic pictures with particles moving along lines and interacting at vertices. Richard Feynman developed these diagrams in the 1940s as a way to visualize and calculate quantum processes. They're not meant to be literal pictures of what's happening, but rather bookkeeping devices for calculating quantum amplitudes. When we say virtual particles exist between interactions, what we really mean is that the quantum fields are in superposition states that include all possible intermediate particle configurations. A virtual particle is a mathematical term in a quantum calculation representing a possible intermediate state in a quantum process. But here's what makes them virtual rather than real. They don't satisfy the normal energy-momentum relationship that real particles must obey. For a real particle, the energy and momentum must be related by Einstein's equation E superscript 2 equals Pc superscript 2 plus mc superscript 2 superscript 2. We say real particles are on shell because they lie on this energy-momentum shell. Virtual particles, on the other hand, are off shell. They can have any energy-momentum relationship, violating what we normally consider the laws of physics, but only temporarily, only internally within a quantum process, and only in a way consistent with the uncertainty principle. Let me give you a concrete example. Consider the electromagnetic force between two electrons. Classically, we'd say the electrons repel each other because they both have negative charge. But in quantum electrodynamics, we describe this repulsion as an exchange of virtual photons. One electron emits a virtual photon, and the other absorbs it, and this exchange mediates the force between them. These virtual photons aren't real photons that you could detect. They exist for such a short time that they can't be directly observed. They're the quantum mechanical description of the electromagnetic field between the electrons. Yet their effects, the force between the electrons, are completely real and measurable. Now, let's think about what this means for the vacuum. At every point in space, quantum fields are fluctuating. These fluctuations can be thought of as virtual particles appearing and disappearing. An electron-positron pair might spontaneously appear, exist for 10 superscript 2 superscript 1 seconds, and then annihilate. A virtual photon might appear and disappear. Quark-antiquark pairs pop in and out of existence. The vacuum is like a quantum foam, constantly churning with virtual particle activity. John Wheeler, one of the pioneers of quantum gravity, called this quantum foam. He imagined that at the smallest scales, around the Planck length of 10 superscript 3 meters, space-time itself might be foaming and fluctuating due to quantum effects. But how do we know this isn't just mathematical fantasy? How do we know these virtual particles correspond to anything real. This is where experiments like the Casimir Effect come in. But before we get there, let me tell you about another fascinating consequence of vacuum fluctuations: the Hawking radiation from black holes. Stephen Hawking proposed in 1974 that black holes aren't completely black. They actually emit radiation due to quantum effects near the event horizon. Here's the simplified picture. Virtual particle pairs are constantly appearing and disappearing everywhere, including right at the edge of a black hole's event horizon. Normally, these pairs quickly annihilate. But near a black hole, something remarkable can happen. If a virtual particle pair appears right at the event horizon, one particle might fall into the black hole while the other escapes to infinity. The particle that escapes becomes real. It's no longer virtual because it's no longer part of a temporary quantum fluctuation. It's been promoted to reality by the extreme conditions near the black hole. The result is that the black hole appears to emit radiation, slowly evaporating over time. This Hawking radiation has never been directly observed from astrophysical black holes. The effect is far too weak. But it's been observed in analog systems like sonic black holes and fluid dynamics, lending support to Hawking's prediction. And it's all due to vacuum fluctuations and virtual particles. Another important concept related to virtual particles is vacuum polarization. When a real electron passes through the vacuum, it polarizes the virtual particle pairs around it. Virtual electron-positron pairs orient themselves in response to the real electron's charge. The virtual positrons are attracted closer, while the virtual electrons are repelled. This creates a screening effect, where the effective charge of the electron depends on how close you are to it. At large distances, you see a reduced effective charge because of this screening. But as you get closer to the electron, you penetrate through the cloud of virtual particles and see more of the bare charge. This is called the running of the coupling constant, and it's been precisely measured in particle physics experiments. The vacuum isn't just a passive background. It actively modifies how particles interact. Now we need to talk about zero-point energy, because it's intimately connected to vacuum fluctuations and it's crucial for understanding the Casimir effect. Zero-point energy is the lowest possible energy that a quantum system can have. But crucially, it's not zero. Let's start with a simple example: the quantum harmonic oscillator. This is a basic model in quantum mechanics, representing a particle bound by a restoring force, like a mass on a spring. In classical physics, if you put the mass at rest at the equilibrium position, it has zero energy. But quantum mechanics says otherwise. Due to the uncertainty principle, the particle can't have both zero position uncertainty and zero momentum uncertainty simultaneously. Even in its ground state, its lowest energy state, the particle must have some residual motion, some quantum jittering. This gives it a minimum energy of 1/2 omega, where omega is the oscillation frequency. This is the zero-point energy of the harmonic oscillator. Now extend this idea to quantum fields. Each mode of a quantum field, each possible wavelength and direction of vibration, behaves like a quantum harmonic oscillator. And each of these modes has its own zero-point energy. The total zero-point energy of the vacuum is the sum of the zero-point energies of all possible field modes at all possible wavelengths in all possible directions. When you try to calculate this sum, you run into a problem. It's infinite. There are infinitely many possible modes, and they each contribute energy, so the total energy diverges to infinity. This is the vacuum catastrophe I mentioned earlier. Physicists handle this infinity through renormalization. We argue that we can't measure absolute energy, only energy differences, so we subtract away the infinite part and focus on measurable differences. This works mathematically, but it leaves us with deep conceptual questions about what's really going on with vacuum energy. Despite these theoretical puzzles, zero-point energy has real, measurable effects. One of the most striking is the Casimir Effect, which we'll discuss in detail soon. But zero-point energy also affects chemistry and materials science. Consider liquid helium-4. At atmospheric pressure, helium remains liquid down to absolute zero temperature. It never freezes. Why? The atoms are so light that their zero-point kinetic energy, their quantum jittering, is large enough to overcome the attractive forces that would normally cause solidification. The zero-point motion keeps the helium liquid even at the coldest possible temperature. Zero-point energy also plays a role in the structure of atomic nuclei, the properties of superconductors, and even the stability of white dwarf stars and neutron stars. It's not just a theoretical curiosity. It's a fundamental aspect of quantum reality that has practical consequences throughout physics. Now we arrive at one of the most elegant and profound demonstrations of vacuum fluctuations, the Casimir Effect. This phenomenon, predicted in 1948 by Dutch physicist Hendrik Casimir, provides direct experimental evidence that the quantum vacuum is real and that it exerts measurable forces. Hendrik Casimir was working at the Philips Research Laboratories in the Netherlands when he made his remarkable prediction. He was actually investigating a different problem: the attractive forces between colloidal particles in a liquid, when he stumbled upon something unexpected. His colleague Dirk Polder had been calculating van der Waals forces, and together they discovered that at large distances, these forces had a different behavior than expected. This led Casimir to consider what would happen with two uncharged metallic plates in a vacuum. The setup is deceptively simple. Take two perfectly flat, parallel, uncharged metallic plates and place them very close together in a vacuum. We're talking distances of micrometers or nanometers. Classical physics predicts nothing should happen. The plates are uncharged, so there's no electrostatic force. There's nothing between them, so there's no pressure. They should just sit there unaffected by each other. But Casimir's quantum mechanical calculation predicted something astonishing. The plates should attract each other. There should be a force pulling them together, arising from nothing but the quantum vacuum itself. How is this possible? Let me explain the physics step by step. Remember that the vacuum is filled with quantum fluctuations, virtual photons constantly appearing and disappearing at all possible wavelengths and frequencies. These vacuum fluctuations of the electromagnetic field exist everywhere in space, creating what we call the zero-point energy of the electromagnetic field. Now, here's the key insight. The metallic plates impose boundary conditions on the electromagnetic field. The electric field must vanish at the surface of a perfect conductor. This means that not all wavelengths of virtual photons can exist between the plates. Only certain discrete wavelengths that fit exactly between the plates, wavelengths where an integer number of half wavelengths equals the plate separation, can exist in the gap. Think of it like standing waves on a guitar string. The string is fixed at both ends, so only certain vibration modes are possible. Those where the wavelength fits perfectly between the fixed points. Wavelengths that don't fit these conditions simply can't exist on that string. The same principle applies to the electromagnetic field between the Casimir plates. Outside the plates, however, there are no such restrictions. Virtual photons of all wavelengths continue to appear and disappear freely in the surrounding vacuum. This creates an asymmetry. There are fewer vacuum fluctuation modes between the plates than outside them. Now, each fluctuation mode contributes to the energy of the vacuum and exerts a radiation pressure. With fewer modes between the plates than outside, there's less vacuum pressure pushing the plates apart from the inside than pushing them together from the outside. The result is a net attractive force, the Casimir force. Casimir calculated that this force should be proportional to the area of the plates and inversely proportional to the fourth power of their separation. Mathematically, the force per unit area is F c, whereas the reduced Planck constant, c, is the speed of light, and d is the separation between the plates. The negative sign indicates attraction. Notice that the force depends on fundamental constants of nature, Planck's constant and the speed of light, but not on the charge or mass of the plates. This is a purely quantum electromagnetic effect, arising from the structure of the vacuum itself. Let me give you some numbers to make this concrete. For two plates with an area of 1 square centimeter separated by 1 micrometer, 1,000th of a millimeter, the Casimir force is about 0.013 dynes, or roughly the weight of a water droplet half a millimeter in diameter. That might not sound like much, but remember, this force comes from absolutely nothing, from the modification of empty space between the plates. As you bring the plates closer together, the force increases dramatically because of that fourth power dependence. At a separation of 100 nanometers, about 1,000th the thickness of a human hair, the force per unit area is about 1 Pascal, comparable to atmosphere pressure. At 10 nanometers, it's 10,000 pascals, or about 1/10 of atmosphere pressure. These are substantial forces at microscopic scales. When Casimir first published his prediction in 1948, it was met with skepticism. Virtual particles? Vacuum energy? Forces from nothing? It seemed too strange to be true. But Casimir was confident in his mathematics, and he predicted that the effect could be measured experimentally. The first experimental confirmation came in 1958, when Marcus Sparnay, also at Philips, attempted to measure the Casimir force. Sparnay's experiments were challenging. He was trying to measure incredibly tiny forces between plates that had to be extraordinarily flat and parallel. His results were consistent with Casimir's prediction, but the experimental uncertainties were large, about 100%. It was suggestive but not conclusive. The breakthrough came in 1997, when Stephen Lamoureux at the University of Washington performed a much more precise experiment. Instead of using two plates, Lamoureux used a plate and a sphere, which simplified the alignment issues. He measured the force as a function of distance and found excellent agreement with Casimir's prediction, within 5% accuracy. This was the first truly convincing experimental confirmation of the Casimir effect. Since then, numerous experiments have confirmed the Casimir effect with increasing precision. In 2001, Umar Mohiddin and Anushree Roy at the University of California, Riverside, achieved even better precision using atomic force microscopy techniques. They measured the Casimir force between a gold-coated sphere and a flat plate with uncertainties of just 1%. Their results agreed beautifully with theoretical predictions. Modern experiments have pushed the precision even further, confirming not just the basic Casimir effect, but also subtle corrections due to finite conductivity, surface roughness, and temperature. Every test has confirmed the quantum vacuum picture. Let's dig deeper into the physics of the Casimir effect, because there are several fascinating aspects we haven't explored yet. First, I want to address a common misconception. The Casimir effect is often explained as a radiation pressure from vacuum fluctuations, with more pressure outside the plates than inside. While this is a useful intuitive picture, it's not quite the whole story. A more sophisticated understanding comes from calculating the change in vacuum energy when you insert the plates. In quantum field theory, we calculate the total zero-point energy of all the electromagnetic field modes. When you introduce the plates, you change which modes are allowed. Some modes that existed before are now forbidden between the plates, while new, quantized modes appear. The total change in vacuum energy depends on the plate separation. As you change the separation, the vacuum energy changes, and the derivative of energy with respect to distance gives you the force. This might sound like mathematical hair splitting, but it leads to important insights. The Casimir effect isn't just about forces, it's about vacuum energy being a real, physical thing that depends on boundary conditions. The vacuum energy has measurable consequences. Another fascinating aspect is the role of the plates themselves. We've been assuming perfect conductors, but real materials aren't perfect. They have finite conductivity, and this affects the Casimir force. The better the conductor, the closer the force matches Casimir's ideal prediction. For poor conductors or dielectrics, the force is modified. In fact, you can have Casimir-like effects with all sorts of boundary conditions, not just conducting plates. Any situation where you modify the allowed modes of a quantum field can produce similar effects. There's a Casimir effect for scalar fields, for fermion fields, even for fields in curved spacetime. The basic principle is always the same. Restrict the quantum fluctuations, and you get real, measurable forces and energy shifts. Temperature also plays a role, though at small separations and room temperature, it's usually negligible. At larger separations or higher temperatures, thermal fluctuations of the electromagnetic field start to dominate over quantum zero-point fluctuations. The force then transitions from the T=0 Casimir force to a classical thermal force. Experiments have confirmed this temperature-dependent transition as well. One of the most intriguing questions about the Casimir effect is whether it could ever be used as an energy source. After all, the force does work when the plates come together. Are we extracting energy from the vacuum? The answer is subtle. Yes, the Casimir force does work as the plates approach, and this energy comes from the reduction in vacuum energy as the plates get closer. But to reset the system, to pull the plates apart again, you have to do work against the Casimir force. The total cycle doesn't give you free energy. You can't build a perpetual motion machine from the Casimir effect. However, the vacuum energy isn't completely inaccessible. In a sense, the Casimir effect represents a conversion of vacuum energy into usable mechanical work. It's not that we're creating energy from nothing. We're changing the configuration of the vacuum and extracting energy from that change. But maintaining any practical engine based on this would require energy input to reset the system. Now, let's talk about some variations and related effects. The Casimir effect I've described is the static Casimir effect, a force between stationary plates. But there's also a dynamic Casimir effect, predicted by Gerald Moore in 1970. The dynamic Casimir effect occurs when you rapidly change the boundary conditions of a quantum field. Imagine you have a cavity with moving walls, where you rapidly change the properties of a material. If you do this fast enough and in the right way, you can actually create real photons from the vacuum fluctuations. Virtual photons get promoted to real photons by the changing boundary conditions. This might sound like science fiction, but it was experimentally demonstrated in 2011 by a group at Chalmers University in Sweden. They used a superconducting circuit with a squid superconducting quantum interference device that effectively acted like a mirror moving at a significant fraction of the speed of light. By rapidly modulating the properties of this mirror, they created real photons from the vacuum. The vacuum literally glowed when they shook it hard enough. This experiment was a stunning confirmation that vacuum fluctuations are not just theoretical constructs, but real, manipulable aspects of physical reality. The Casimir effect isn't limited to parallel plates. It occurs in many different geometries, and each configuration reveals something interesting about the quantum vacuum. Consider a spherical shell, a hollow conducting sphere. The interior of the sphere has different allowed electromagnetic modes than the exterior. This creates a Casimir pressure on the shell. Interestingly, the pressure tends to compress the shell inward. The vacuum is literally squeezing the sphere from all sides, though the effect is incredibly small for macroscopic spheres. For cylindrical geometries, the Casimir effect produces both radial and longitudinal forces. A conducting cylinder experiences forces trying to collapse it radially and compress it axially. The mathematics becomes more complex, but the underlying physics is the same. The modification of vacuum fluctuations by boundary conditions produces real forces. One of the most interesting geometries is the Casimir effect between an atom and a surface. When an atom approaches a conducting plate, it experiences a Casimir polar force. At close distances, this is essentially the van der Waals force, the interaction between the atom's fluctuating dipole moment and its image in the conductor. At larger distances, retardation effects become important because electromagnetic interactions propagate at the speed of light, and the force transitions to a different distance dependence. This atom surface Casimir polar force has been measured experimentally using cold atom techniques. Researchers can measure how the energy levels of atoms shift as they approach a surface, or they can measure the force directly by observing the trajectory of atoms in atomic beams or the deflection of Bose-Einstein condensates near surfaces. What about the Casimir force between atoms themselves? This is essentially what van der Waals forces are at the quantum level. Two atoms, even if they're both electrically neutral, experience an attractive force due to correlated fluctuations in their electron clouds. Each atom has a fluctuating dipole moment due to quantum fluctuations, and these fluctuations become correlated when the atoms are close together, leading to attraction. This quantum mechanical origin of van der Waals forces was worked out by Fritz London in 1930, before Casimir's work. In fact, understanding van der Waals forces at large separations was what led Casimir to his prediction in the first place. The Casimir effect and van der Waals forces are deeply related. They're both manifestations of quantum vacuum fluctuations interacting with matter. These forces might seem esoteric, but they're crucial for understanding chemistry and biology. Van der Waals forces help determine the three-dimensional structure of proteins, the stickiness of gecko feet, the properties of materials, and countless other phenomena. They're quantum vacuum effects in action at everyday scales. Now, here's something really interesting. The Casimir force isn't always attractive. Depending on the materials and geometry, you can get repulsive Casimir forces. This was predicted theoretically and confirmed experimentally. The key is to use 3 different materials with the right dielectric properties. Imagine you have 2 plates of different materials immersed in a fluid. If you choose the materials carefully, so that the dielectric constant of the fluid is between the dielectric constants of the two plates. The Casimir force can become repulsive. The plates push apart rather than pulling together. This repulsive Casimir effect was demonstrated experimentally in 2009 by Jeremy Munday and Federico Capasso at Harvard. They used a gold plate and a silica plate immersed in bromobenzene, and they measured a repulsive force consistent with theoretical predictions. Why does this happen? It comes down to the different ways that different materials modify the electromagnetic field modes. With the right combination of materials, you can arrange for there to be more vacuum pressure between the objects and outside them, reversing the usual Casimir attraction. This discovery opened up exciting possibilities. Could we use repulsive Casimir forces for quantum levitation? Could we build frictionless nanomachines? The forces are still tiny, but at small enough scales, they might be significant. As we've pushed technology to smaller and smaller scales, the Casimir effect has transitioned from a curiosity to a practical concern. In the world of nanotechnology and microelectromechanical systems, MEMS, Casimir forces can't be ignored. MEMS devices are microscopic machines with moving parts, tiny gears, cantilevers, springs, and actuators, often just micrometers in size. These devices are everywhere in modern technology, in accelerometers that detect when you drop your phone, in the tiny mirrors that create images in digital projectors, in pressure sensors, gyroscopes, and countless other applications. As MEMS devices have gotten smaller, engineers have encountered a problem. Components that are supposed to move freely sometimes stick together. This phenomenon, called stiction, can be caused by various effects, but at small enough separations, the Casimir force is a significant contributor. Imagine a tiny cantilever beam hovering just nanometers above a substrate. The Casimir force pulls them together. If the force is strong enough, it can overcome the restoring force of the beam and cause it to collapse onto the substrate, where it might stick due to Casimir and van der Waals forces. This can permanently disable the device. Engineers designing MEMS devices now have to take Casimir forces into account. They need to ensure that components don't get close enough for these forces to cause problems, or they need to design structures stiff enough to resist Casimir attraction. It's a remarkable situation. Engineers designing practical devices have to consider quantum vacuum fluctuations in their calculations. But the Casimir effect isn't just a problem to be solved, it also offers opportunities. Some researchers are exploring whether Casimir forces could be harnessed for actuation in nanomachines. Could we build switches or actuators powered by vacuum fluctuations? Could we use the repulsive Casimir effect to create frictionless bearings or levitating components? These ideas are still mostly theoretical, but they're being actively researched. The Casimir effect might transition from being a nuisance in nanotechnology to being a useful tool. Another area where the Casimir effect becomes important is in understanding fundamental forces at short distances. When you're trying to test Newton's law of gravitation at micrometer scales, or searching for new fundamental forces, you have to carefully account for Casimir and van der Waals forces, which can easily dominate gravity at these scales. Some experiments searching for deviations from known physics, looking for evidence of extra dimensions, for instance, or new forces predicted by string theory, have to include very precise calculations of Casimir effects to distinguish any new physics from quantum vacuum effects. The Casimir effect also plays a role in atomic force microscopy, AFM, a crucial tool in nanotechnology. AFM works by bringing a sharp tip very close to a surface and measuring the forces between them. At the smallest distances, Casimir forces contribute significantly to what the microscope measures. Understanding these forces is essential for interpreting AFM data correctly. In recent years, researchers have started to explore Casimir effects in more exotic materials. What happens with graphene, a single layer of carbon atoms? Graphene has unique electromagnetic properties, and the Casimir force between graphene sheets differs from that between ordinary conductors. Several groups have measured these effects, finding good agreement with theoretical predictions that account for graphene's special properties. What about metamaterials? Engineered materials with electromagnetic properties not found in nature. Could we design metamaterials to enhance or suppress Casimir forces in useful ways? Could we create materials with zero or even negative vacuum energy density in certain regions? These questions are at the frontier of current research. Now let's shift gears and think about the Casimir effect on cosmic scales. This might seem like a strange jump. We've been talking about forces between plates separated by micrometers, and now we're going to talk about the entire universe. But there are deep connections between vacuum energy, the Casimir effect, and cosmology. Remember that the Casimir effect arises from the change in vacuum energy when you impose boundary conditions on quantum fields. The total vacuum energy is formally infinite, but differences in vacuum energy between different configurations are finite and measurable. This raises a profound question. Does the vacuum energy of the entire universe have physical consequences? The answer appears to be yes, and it's connected to one of the biggest mysteries in modern cosmology: dark energy. In 1998, two teams of astronomers made a startling discovery. By observing distant supernovae, they found that the expansion of the universe is accelerating. Not just expanding, but expanding faster and faster. This was completely unexpected. The gravitational attraction of all the matter in the universe should be slowing down the expansion, not speeding it up. To explain this acceleration, physicists introduced the concept of dark energy, a mysterious form of energy that permeates all of space and causes a kind of cosmic repulsion. The simplest form of dark energy is Einstein's cosmological constant, which is mathematically equivalent to a constant energy density of the vacuum. Here's where the Casimir effect becomes relevant. If the vacuum has a real energy density, it should gravitate according to general relativity. Vacuum energy acts like a cosmological constant. In principle, the zero-point energy of all quantum fields should contribute to the vacuum energy density of the universe. But there's a catastrophic problem. When you try to calculate the vacuum energy density from quantum field theory, you get a value that's about 10 to 120 times larger than the observed dark energy density. This is the worst prediction in the history of physics, off by 120 orders of magnitude. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. Why is the vacuum energy density so incredibly small compared to what quantum field theory predicts? Or alternatively, why is there such a huge cancellation that leaves only a tiny residual vacuum energy? The Casimir effect tells us that vacuum energy is real and has measurable consequences. But somehow, on cosmic scales, almost all of this vacuum energy must cancel out or be screened in some way we don't understand. Various solutions have been proposed: supersymmetry, which would cause bosonic and fermionic contributions to cancel; anthropic reasoning in a multiverse; modifications to quantum field theory, or general relativity. But none of these solutions is widely accepted. There's another connection between the Casimir effect and cosmology, the structure of the early universe. During inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, quantum fluctuations in the inflating field were stretched to cosmic scales. These quantum fluctuations became the seeds for all the structure we see in the universe today. Galaxies, clusters of galaxies, the cosmic microwave background variations, everything. This is conceptually similar to the Casimir effect. Quantum fluctuations, normally microscopic and virtual, can become real and macroscopic under the right conditions. In the Casimir effect, the boundary conditions of conducting plates modify and give physical consequence to quantum fluctuations. In inflation, the rapid expansion of space-time stretches quantum fluctuations and makes them real. The cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today, carries the imprint of these quantum fluctuations from inflation. When we look at the tiny temperature variations across the sky in a microwave background, we're literally seeing quantum mechanics written on the sky. Observations from satellites like WMAP and Planck have measured these fluctuations with exquisite precision, and they match the predictions of quantum field theory in an expanding universe. So in a very real sense, the large-scale structure of the universe, the distribution of galaxies, the pattern of light and dark in the microwave background, perhaps even the fact that we exist, all traces back to quantum vacuum fluctuations, the same physics that underlies the Casimir effect. Some cosmologists have even speculated about Casimir effects in the universe as a whole. If the universe has a specific topology, if space wraps around on itself in some way, or if there are extra dimensions as string theory suggests, this could impose boundary conditions on quantum fields and produce universe-scale Casimir effects. These effects might contribute to dark energy or modify the expansion history of the universe. These ideas are highly speculative, but they illustrate how the physics of vacuum fluctuations might connect the very smallest scales of quantum mechanics to the largest scales of cosmology. Let's step back and think about what the Casimir effect and vacuum fluctuations mean philosophically. These phenomena challenge some of our deepest intuitions about reality. First, there's the nature of nothingness itself. Humans have contemplated the concept of nothing for millennia. Philosophers from Parmenides to Heidegger have grappled with the paradoxes of nothingness. Can nothing exist? Is nothing something? Quantum mechanics gives us a definitive answer. True nothingness is impossible. Even in a perfect vacuum, devoid of all particles and radiation, the quantum fields are still there, fluctuating, carrying energy, exerting forces. The vacuum is not nothing. It's a very specific quantum state with definite properties. You can't remove the quantum fields. They're built into the fabric of reality itself. This has implications for cosmology and for questions about why there's something rather than nothing. If the vacuum state of quantum fields is the most nothing that can exist, and yet it already has structure and energy, then perhaps something is the default state and nothing is actually impossible. There's also the question of what's real. Virtual particles don't last long enough to be observed directly. They're off-shell, violating the normal energy-momentum relationship. Are they real, or are they just mathematical artifacts of our calculations? The Casimir effect gives us an answer. They're real in the sense that they have measurable consequences. You can't observe a virtual photon directly, but you can feel the force it mediates. The boundary between real and virtual becomes blurred. Perhaps reality isn't binary. Perhaps there are degrees of reality or different modes of existence. This touches on fundamental questions in the philosophy of science. What does it mean for something to be real? Is it enough that something appears in our best theories and has observable consequences? Or must it be directly observable to count as real? Quantum field theory suggests a deeply relational view of reality. Particles aren't fundamental objects floating in empty space. Instead, fields are fundamental, and particles are excitations of these fields. But even the fields aren't independent entities. They're defined by their interactions, by the symmetries they obey, by the boundary conditions imposed on them. The Casimir effect exemplifies this relational nature. The force between the plates isn't caused by something traveling between them. It's not a classical action at a distance. It's a change in the quantum state of the electromagnetic field due to the presence of the plates. The field, the plates, and the force form an indivisible whole. This has echoes in various philosophical traditions. Buddhist philosophy speaks of emptiness, sunyata, and dependent origination. The idea that things don't have inherent independent existence, but arise in dependence on other things. While it would be wrong to claim that quantum field theory proves Buddhist philosophy, there are intriguing resonances. The vacuum is empty of particles yet full of potential and activity. Things arise in dependence on boundary conditions and interactions. So let's bring this all together. What we learned today, we've discovered that empty space is not empty at all. The quantum vacuum is a seething ocean of energy, with virtual particles constantly appearing and disappearing, borrowing energy from the uncertainty principle and paying it back in fractions of a second. This isn't philosophical speculation. It's experimentally verified reality. The Casimir effect proves this beyond any doubt. Two metal plates in a vacuum attract each other purely because of quantum fluctuations. The vacuum itself pushes them together. This has been measured with extraordinary precision, confirming that vacuum energy is real and has physical consequences. These vacuum fluctuations affect everything from the structure of atoms to the fate of the universe. They explain the Lamb shift, spontaneous emission, Hawking radiation from black holes, and possibly even dark energy. They're crucial for understanding nanotechnology, and they connect the smallest quantum scales to the largest cosmological scales. Perhaps most profoundly, vacuum fluctuations force us to rethink what we mean by nothing and something by real and virtual by empty and full. The universe is far stranger and more wonderful than our everyday intuition suggests. The next time you look at empty space between your hands, in a room, or up at the night sky, remember, it's not empty at all. It's alive with quantum activity, humming with zero-point energy, a cosmic symphony playing at frequencies we can't hear, but whose effects we can measure and feel. That's the quantum universe we live in. That's the reality revealed by the Casimir Effect. Thank you so much for watching Quantumize Yin. If you enjoyed diving deep into the quantum vacuum with me today, please hit that like button and subscribe for more explorations of quantum physics.